Today we want to look at optimization. It is a new topic and it is not in your book as a section, but it fits right in with what we're doing. And at this point, doing derivatives and trying to set derivatives equal to zero to find maxes and mins and that type of thing. So we're going to put it in at this point. Our whole goal is to use calculus to identify maxima and minima on application problems. Anytime you hear application problems, that means they're going to be real-world problems. Problems where the situation is, well, let's say a word problem, okay? So you're going to have a ton of word problems. That's just all there is to it. So here we go. Let's see what we can learn. Okay, this is from Algebra 2. This was a pretty simple problem at that point. You had a farmer, he wants to fence in an area for his cattle with the 36 feet of fencing material that he has on hand. He doesn't want to buy any more. One side of the area will not need to be fenced because it is bounded by the side of the barn. What length and width will produce the maximum area? Now, first thing, let's draw our picture. And I do want us to think, if you read this in a book, a lot of times they'll say it's a three-sided fence bounded by a river, but I mean that doesn't make any sense because the cattle can stick it out. So let's have a barn there, 3 sides of a fence, and I have a total of 36 feet of fencing. Okay, well, to figure that out, what we did on these, we know that all 3 sides, this, have got to add up to be 36. I just don't know what they are. But I know that if this side is x, this side is x, then this right here would be 36 minus 2x. And you've got to be sure that you understand that. Okay? And then I'm wanting to produce the maximum area. Area of a rectangle is length times width. So my area on this is going to be x times 36 minus 2x. So you get a equals 36x minus 2x squared. From there, what you did was you recognized that this was a parabola that was turned upside down, and so you needed to be able to find the vertex. And wherever the vertex was, the x value was going to be your width right here, and the y value was going to be your area. Okay, that maximum area, because that is obviously a maximum. Okay, well, the way that we did that, because we didn't have calculus at that point, we had our little formula of negative b over 2a and then f at negative b over 2a in order to find that ordered pair. Hopefully we remember that, but how much nicer is it with calculus to be able to recognize, oh, at a max, I have a horizontal tangent of 0. So all I have to do, if I have a horizontal tangent, that's the slope of the tangent line being equal to 0. So if I come back up here and I do dA dx, because I'm taking my derivative of the area with respect to my sides x, that's going to be 36 minus 4x, set it equal to 0 because the slope of my horizontal tangent line is 0. Solve and you get x equals 9. So that tells me that my 2 vertical sides over here are 9, and that my other side is 36 minus 2 times 9. Okay, so I've got 36 minus 2 times 9, which is 18. Okay, so what length and width will produce the maximum area? Again, this was in feet, so I want 9 feet by 18 feet. Okay, and that will do that. That gives you your maximum area. Your x value needs to be 9. I was looking to see if I had mixed something one side of the area. Nope, length and width. So there's my length and my width, 9 feet by 18 feet. Okay, so it's not so bad. We're going to set up problems, take the derivative, set equal to 0, find max or min. Shouldn't be a big deal. I'm saving the question mark for tomorrow in class, so be sure that you've worked through these problems so you can do it. Okay, We have a minimum area problem. Okay, instead of a max, we're going to look at a min. Problem says a rectangular page is to contain 40 square inches of print. The margins are to be 1/2 inch on each side. Find the dimensions of the page such that the least amount of paper is used. Well, first thing on these is always draw you a picture. So what I have is a page that has a printed area on it, like that. 40 square inches of print. So this right here is 40 inches squared. The margins are to be 1/2 inch on each side. So this is 1/2 inch. And this one down here is 1/2, and same thing here, same thing here. Okay, all your margins are 1/2 inch. I'm supposed to find the dimensions of the page such that the least amount of paper is used. If I know that this area right here is 40 square inches, then I know that the area of the printed part, I'm just going to put a P for printed, equals length times width equals 40. Okay. So then I can solve for either length or width, it doesn't matter. And let's just say W equals 40 over L. And I'm going to need to use that. I want the dimensions so that the least amount of paper, I'm still looking at area, but my area is going to be a little bit different here. I don't know exactly my length right here. I don't know exactly my width right here. I just know that multiplied together they give me 40, but I'm still going to add in these halves. Okay, so what I have overall for the area of my entire page is going to be my length plus 1 inch on each side. Okay, I've got my length right here plus 1/2 inch plus 1/2 inch. So that's going to give me L plus 1 times, going the other way, I've got my width plus 1. Okay. Well, now you know why we solved down here, W equals 40 over L. So that's going to make my area equal L plus 1 times 40 over L plus 1. Okay, I know that to find dimensions so that least or most, that's always going to be a max or a min. I need my derivative set equal to 0. You have a choice. You can either go through and do your product rule here, or you can do FOIL and then do it. I'm going to go ahead and do FOIL at this point. It's not really a big deal one way or the other. First, it's going to give me 40. Outside is L. Inside is 40 over L. And my last is 1. Okay, so first, outside, inside, last. When you take your derivative there, you get dA dx, dA dL, because you're taking it with respect to L, equals derivative of constant, that's gone to 0. Derivative of L, that's going to be a 1. Derivative of 40 over L, remember that's 40 L to the negative 1, so that's minus 40 over L squared. And the derivative of 1 goes to 0 as well. Okay, so set that equal to 0 now and solve. And I have 40 over L squared. Whoops, sorry, not sure why I put that little line under there. 40 over L squared equals 1. Okay. And I'm still doing strange things for some reason, and I haven't got a clue. Let me move up here and give myself some room and see if I can think better. 40 over L squared equals 1. How about that? Okay, so now then L squared equals 40. And so L equals, technically, plus or minus the square root of 40, but that doesn't make any sense at all because you can't have negative length. So we'll go with the positive square root of 40, which is really 2 square root of 10. Okay. Well, if I put that back into my W equals 40 over L, that's 40 over the square root of 40, which is also the square root of 40, which is 2 square root of 10. So my length and my width are the same. So a square sheet of paper is the best one to be able to use things that use the maximum amount of area, the least amount of paper with the maximum amount of area. Okay, but it said find the dimensions of the page. It didn't say find the dimensions of the printed area. 2 square root of 10 and 2 square root of 10, those are the dimensions of the printed area. I've got to go back because my overall page is right here, right? I need my length plus 1 and my width plus 1. So my length was 2 square root of 10 plus 1. And this is inches by 2 square root of 10 plus 1 inches in width. So there's my length times my width. There's my solution. Okay. If you've got your calculator, plug it in and give me the decimal. The decimal's fine. I just don't have mine handy right here. So there we go. Okay, we want to add a little bit of a twist in that we're going to add cost into it. Things like squares, I mean, those are always going to be your most economical in terms of area until you start adding in things like cost of something per square inch and having things have a different value. So we want a little bit of a challenge problem here. We have a cylindrical metal container that is open at the top. That's a big deal. That means I do not have any type of metal up at the top. It's supposed to have a capacity of 24 pi cubic inches. That's an important thing right there. It means my volume is 24 pi cubic inches. Cost of the material used for the bottom of the container is 15 cents per square inch. Cost of the material used for the curved part, that's the ones that go around the edges. Like if you have a can, it's the sides of the can. Find the dimensions that will minimize the cost of the material and find the minimum cost. Okay, well, we need to know what the surface area of a cylinder is, and your surface area, since this is open at the top, I have one circle at the bottom, that's going to be pi r squared, and I have my side, which happens to be, my sides, if you slice down a cylinder and open it up, it's a rectangle. The length of the rectangle is the circumference, 2 pi r, and the width of the rectangle is the height of your can. And so if you slice that and open it up, if you think about it, if not, let me know because we'll talk about it in class on the next class period. Okay, so let me know. All right. I need that. I also need volume. Okay, what's my volume on a cylindrical metal container? Your volume on that is going to be pi r squared h. On the AP exam, they do give you these formulas. They don't want anything non-calculus related to keep you from getting your answers right. So, volume is 24 pi. We will plug that in right there. Equals pi r squared h. If I divide by pi on that, then both of those would cancel out. And so I have 24 equals r squared h. Looking back up at my surface area, which is the thing that I want to minimize, I want to minimize this equation right here, not just this piece of it, but the entire equation there. I have pi r squared, 2 pi r, and h. That h is kind of random thrown in there. I can't take these derivatives right now with two different variables in there. We'll get there, but we can't do it right this minute. So I need to get rid of that h. I do that by looking right down here at the equation that we just found. I solved that for h. h is going to equal 24 over r squared. So now then I go back into my surface area equation, and that's going to be pi r squared plus 2 pi times r times 24 over r squared, because that's my h value. Okay, well, I'll have an r cancel there, so my final surface area formula here will be pi r squared plus 48 pi over r. Again, finding the cost. Okay, I don't want just the dimensions this time. I want to minimize the cost of doing this. And so that takes on a whole new thing. It's not that I'm just taking my surface area and setting it equal to 0. Okay, I've got to go back up here. The cost of the material used for the bottom of the container is 15 cents per square inch. So what I'm writing now is a cost equation, and I am going to multiply 15 cents times the area of the bottom. This is still my surface area equation, but I'm going to add in the cost, or technically multiply the cost, plus 0.05 for the cost per square inch of the curved part, which happens to be 48 pi over r. This makes my cost equation be 0.15 pi r squared plus 2.4 pi over r. Okay, so from there we'll take our derivative, because I'm wanting to minimize the cost. So 2 times 0.15, I get 0.3 pi r. Okay, again on this one right here, the r is r to the negative 1, so minus 2.4 pi over r squared. And I'm going to set it equal to 0. Okay, so getting a common denominator here, multiply all the way through by r squared. I have 0.3 pi r cubed minus 2.4 pi all over r squared equals 0. Whenever you are working through these problems, you know, if you're going to have it equal to 0, all you're going to have to worry about is that numerator right there. So I can factor out a 0.3 pi from my numerator. Leaves me with r cubed minus 8. The 0.3 pi, when I divide by 0, is going to go away. So I have r cubed minus 8 equals 0, and r cubed, would equal 8, and r equals 2. Now that is not really very good notation, because if you have imaginary numbers or anything like that, then you're losing those by doing it like this, but we know that we're dealing with real numbers. So that gives me my real number answer. So I have r equals 2, and I want to plug that back in to find my h. H is 24 over r squared, so over 2 squared, which 24 over 4 is 6. Okay, so my r, to finish this out, is 2 inches. My radius is 2 inches. My height is 6 inches. It also asks us to find the cost. So to find the cost, you take it and you plug it back in, plug your r back into that equation or the one right underneath it, either one, and you should get on that. Again, I'm without a calculator, so 1.8 pi dollars for your cost, and you can plug that in, and please give me a 2-decimal answer on that since we're talking about money. As we go to the next problem, I want you to realize that we are not going to do this one. This one I really want to do with you in class. It's going to take us a little bit of time and thought. but you can look at it, see if you can at least sketch your picture and figure out what is going on with it. Pause it for a minute, kind of get you some notes jotted down so you don't have to write down so much in class, and we'll see if we can fix this one. We want to, how should this be done if the speed limit is 60 kilometers per hour on the road, 110 kilometers per hour on the highway? We want to build a road, and so let's see if we can find the best way to do that so we can get to the city in the shortest amount of time. Based on our traffic lately, a shorter amount of time and a good road would be a good thing. So anyway, the assignment will be a worksheet that I'll hand you in class. But anyway, hope you've gotten some good notes and made lots of questions, because this stuff is not easy material. Let me know if you need anything. Thanks. Bye, y'all.